Now today we will see uh, some properties of the mm, length function that we have already defined for a for an inner product space, V. So let V be an inner product space over a field F, and then we have defined a length function, or it is called norm of a vector. V belongs to V, as norm of V is the non-negative square root of the inner product V comma V. So this function, it is a function from the inner product space V to the real number set R, defined by this rule. That is norm V equal to root over inner product V comma V. Now if you look at the function, you will see that the first property it has, it is a non-negative function. That is, for every vector V, norm of V will be greater or equal to 0. And if it is 0, then root over inner product V comma V is 0. That is, if and only if inner product V comma V is 0, that is if and only V equal to theta. So the only possibility is V is theta. So this is the first property it has. And the second one is norm of alpha V. So what is norm of alpha V? So if we take it square, then it will be alpha V inner product alpha V comma alpha V. That is alpha bar inner product V comma V. That is mod alpha square inner product V comma V. That means norm alpha V equals to mod alpha inner product V comma V. So that means root over inner product V comma V. So that means mod alpha norm of V. This is true for all V belongs to V and for all alpha belongs to F. Yeah. So this is the second property it has. And the third one is the triangle inequality. That is, for any two vector u and v, if we take the square of u plus v, square of the norm of u plus v, then it will be inner product u plus v comma u plus v. Now just expand it, then it will be inner product u comma u, inner product u comma v, inner product v comma u plus inner product v comma v. And then we have, so inner product u comma u plus inner product v comma v plus inner product u comma v plus inner product u comma v conjugate. So a complex number plus its conjugate, it will be 2 into real part of that complex number. So this is norm u square, this is norm v square, and this is 2 real part of u comma v. Yeah. So that means it is less or equal to norm u square plus norm v square plus 2 into modulus of real part of u comma v, since every real number is less or equal to its modulus. And again, the modulus of real part of this, it will be less or equal to the modulus of the complex number. So therefore, it is norm u square norm v square plus 2 mod inner product u comma v. Since real mod of real part of this is less or equal to modulus of this complex number. As we know, real part of z is less or equal to mod z. Okay. Now, from Cauchy-Schwarz inequality, we have already obtained that it is less or equal to norm u square plus norm v square plus 2 into norm u norm v. So that means it is norm u plus norm v square. So thus we have norm u plus v square is less or equal to norm u plus norm v square. That means taking non-negative square root from both sides, we will have norm u plus v is less or equal to norm u plus norm v. So this is called triangle inequality in a norm in a in an inner product case. Yeah, and this norm is called, so this is called the norm on an inner product space V induced by the inner product function this. Yeah. So thus we see that every inner product space will induce a norm, and this norm will have these three properties. So we are looking for a function which will have these three properties defined on a non-empty set X. Then this function will be defined to be a norm function, and for each vector v, norm v will be called the length of v or norm of the vector v. So we are looking for a general concept of a norm, that is, we have to axiomatize these three conditions, these three properties. So definition will be, let V be a vector space over F, F is equal to R or C. A function denoted by this from the vector space V to R is defined to be a norm on V if number one is norm of V is greater or equal to 0 for all V belongs to capital V, and norm V will be 0 if and only V equal to theta. Number two is norm alpha V equal to mod alpha norm V for all scalars alpha belongs to F, for all vector V belongs to B. Okay. So, and number three is the triangle inequality. That is, for any two vector u and v, norm of u plus v will be less or equal to norm u plus norm v. This is true for all u belongs to, all u comma v belongs to capital V. Yeah. So in this way, we have defined a general concept of a norm which has three basic axioms. Number one, number two, and number three. Yeah. And so any function having these three axiom will be called a norm. So this is a general concept. So any function from a vector space V to R, which will, if it satisfies 1, 2 and 3, then we call this function a norm function, or for each vector V, norm V will be called the norm of the vector V. A vector space V with a norm function is called a normed linear space. A normed linear space, or in abbreviated form, it is it will be written as NLS, that is normed linear space. For example, in R2, if you denote norm of V equal to, in R2, if we define norm V, what is V? V is the point whose coordinates are x and y. So if it is defined as mod x plus mod y, then it will satisfy the axioms of a norm. So this is a norm on R2. And also, uh, we have already a natural, a usual norm on R2, that is norm V equal to norm x plus xy, which is root over of x square plus y square. So this is a usual norm on R2. Similarly, if you are going to talk on higher dimensions Rn, then its usual norm will be root over of x square, x1 square plus x2 square plus xn square, if x1 x2 xn denotes a point. And it should be noted that there exists no inner product on R2 which will, okay, this is very important. Yeah, this norm, now we have seen that, yeah, we have seen that for a for an inner product space V, we can define a norm always, which is norm V equal to root over of inner product V comma V, always. That means every inner product space is a nonlinear space. But but every nonlinear space need not be an inner product space. That means a norm did not induce an inner product on a nonlinear space in general. Okay. For example, so but a norm defined on a vector space need not induce an inner product in general. For example, in R2, norm of V equal to norm of the point xy, that is mod x plus mod y, it will not induce an inner product. For example, this, in which there exists no inner product, there exists no inner product on R2 which will induce that norm, this norm. There exists no inner product on R2 which will induce this norm. And this feature of this So, and this feature of this norm, that is, it will, there exists no inner product on which on R2 which will induce the norm defined by this. And why it is not true? Because it will not satisfy a property which a nonlinear space has, an inner product space has, and which will be called parallelogram law. That is, if a nonlinear space will satisfy parallelogram law, then you can define an inner product which will induce that norm. And for our case, for this norm, parallelogram law doesn't hold. You can check it. So we will talk okay, about parallelogram law. Yeah, in the previous discussion we have already talked about this parallelogram law. That is, for any two vectors, this plus u minus v square equal to 2 norm u square plus norm v square. So this is the parallelogram law, and this law will not be satisfied by this no or not. Okay. So this result uh, should be noted down because it is important. So in a nonlinear space V, the norm on V can be can be induced from an inner product. The norm can be induced from an inner product if and only if the parallelogram law holds. That is, for any two vectors u comma v belongs to capital V, norm u plus v square plus norm u minus v square equal to 2 into norm u square plus norm v square. Now we will not prove this theorem at this stage. We will prove it later in maybe some uh, maybe in the next lecture, that we will prove that in the norm, in a nonlinear space, the norm can be induced from an inner product if and only parallelogram law holds. Okay. Okay. Now we move to explore the concept of a geometrical concept of perpendicularity. That is, in R2 in plane or in space R3, you frequently uh, call two vectors are perpendicular if their angle is pi by 2. But the real fact is that actually two vectors are perpendicular if their inner product is 0. Inner product of that space with respect to this inner product, suppose u and v be the vectors, so u is said to be perpendicular to v if their inner product is 0. That is, inner product u comma v is 0. So this is the fact. And with this fact, you will have that two vectors are perpendicular if and only if the angle between them will be pi by 2, just by using the definition of angle in terms of inner products. So let us define uh, definition. So two vectors u comma v belongs to v are said to be orthogonal are said to be orthogonal to each other if the inner product u comma v is 0. Or you can say that, or you can say that u is orthogonal to v if u comma v is 0. Now, why so why did I write down this one to each other? Because of the fact that if u comma v is 0, then v comma u will be the conjugate of u comma v, and this is 0. So that is why u and v are said to be orthogonal to each other if and only their inner product is 0. So this is obvious. So u is orthogonal to v means it implies v is also orthogonal to u. And also note that the 0 vector theta is orthogonal to each vector. Zero vector theta is orthogonal to each vector. Okay. Now, if u is orthogonal to v, then we denote it by u perp v. This stands for perpendicularity, perp. Yeah. So u perp v. So this is the notation. And from that one you can write down that theta is theta perp to every vector. Theta is orthogonal to each vector. Yeah. The next definition is like that. Now let us consider a subset of a vector space V. Let W be a subset of V. Then the orthogonal complement of W, which is denoted by W perp and defined as the set of all those vectors in V which are perpendicular to or orthogonal to each vector of W. So the orthogonal complement of a subset W of a vector space V is defined to be the set of all those vectors. Small v belongs to capital V, such that small v is orthogonal to each vector of W. Now, since the 0 vector is orthogonal to each vector, so 0 inner product theta comma W is 0 for all W belongs to capital W, and that means theta belongs to W perp. And it shows that for any subset W perp is non-empty. But it has more properties than a simple non-empty set. That is, it is a subspace of V. Although W is any set, W may be a subspace or not, but W perp is always a subspace of V. Whatever W is, maybe it is a subspace or maybe it is an ordinary subset of the vector space V, but its orthogonal complement will always be a subspace of that vector space. So we will prove it. Okay, so let us prove this one, that so the theorem is, so if W subset of V, then W perf is a subspace of V. Why? Because as if we let as if we let uh, V B1 B2 belongs to W part, then B1 comma W equal to 0, V2 comma W equal to 0 for all W belongs to capital W. And now for any scalar alpha comma beta belongs to F, so alpha V1 plus beta V2 inner product with W equal to alpha 1 alpha V1 W plus beta V2W. Now these two inner products are 0, so that means it is 0. And this is true for all W belongs to capital W, and that means alpha V1 plus beta W belongs to W part. And this proves that W part is a subspace of V. Whether W is a subspace or not, but W part is always a subspace of the vector space V. And being a subspace, it should be noted that the linear span of W, its orthogonal complement will be W perp itself. Since linear span of W is linear span of since linear span of W is is a is the smallest subspace of of the vector space V containing W. So that is why, and W itself and W perf so uh, uh, since the reason is that this is a subspace of V and linear space of W is the smallest subspace of V generated by W. That is, W is a subset of linear span of W. So now, any vector V belongs to LSW perp will have that. So inner product V comma small w equal to 0 for all W belongs to LSW. LSW. Yeah. Now, since W itself is a subset of LSW, so in particular, for every vector of W, inner product of VW is 0 for all W belongs to capital W. and that means V belongs to W park. So therefore, LSW park is a subset of W park. Yeah. Now we need to show that the reverse inequality holds. So let V belongs to W park. So then V comma W equal to 0 for all W belongs to capital W. Now let for any finitely many scalars lambda 1, lambda 2, lambda n. Now lambda 1 W1 plus lambda 2 W2 plus lambda n Wn. So for any finitely many scalars lambda 1, lambda 2, lambda n, lambda 1 W1 plus lambda 2 W2 plus lambda n Wn are always a member of the linear span of W. So this implies the inner product V comma lambda 1 W1 plus lambda 2 W2 plus lambda n Wn. So this will be so lambda 1 bar inner product V comma W1, lambda 2 bar inner product V comma W2 dot lambda n bar inner product V comma Wn. Now since each W1, W2, Wn are members of W, so these inner products are all 0. So this is 0. And this implies inner product V comma W star equal to 0 for all W star belongs to LSW. Yeah. So that means V belongs to LSW perpendicular. So hence the linear span of W has the orthogonal complement as the orthogonal complement of W. Yeah. And also note that for any subset W of the vector space V, W intersection W perp equal to singleton theta. But why? Because as W belongs to W intersection W perp implies inner product let us take it V. So V comma W equal to 0 for all W belongs to capital W. So that means so as V belongs to W itself, so it is V comma V equal to 0. And that means V equal to the null vector theta. And this proves that, so this shows that theta is the only element which is included in the set W intersection W part. Yeah. Now it is your exercise to check that if W1 subset of W2 subset of V then one can check that W2 orthogonal is a subset of W1. And our aim is to show that for a subspace W, now for a subspace W, we are to show that of V, we are to show that V will be represented as a sum of two members, one from W and another from W perp, as W intersection W perp is non-empty. Okay. Now, now let us define to do this uh, representation, that is to express the vector space V as a sum of W plus W perp. So we need to have at our hand some kind of special basis that has some properties. That the one thing is that the set of vectors of that basis. So since it is a basis, so it must be linearly independent. And the other thing is that their norm are one. Their norms are one. And our aim is to show that given any basis, any linearly independent set, you can always construct a basis which are linearly independent and all the vectors are orthogonal to each other and their norms are 1. So we can eventually show that this happens. Yes, for a given linearly independent set, you can always construct a set which are orthogonal, whose vectors are orthogonal to each other and whose norms are 1. Okay. So to establish this result, so let us introduce the concept of orthogonal sets or orthonormal sets, and later we will do this for a basis, that is orthonormal basis, orthogonal basis. So let V be an inner product space, then the set of vectors Vi is called an orthogonal set if for all I comma j inner product Vi comma Vj equal to 0. In addition to this,
স্যার আপনার কথা কিছু শোনা যাচ্ছে না।
hello,
হেডফোন
শুনতে
লাগাস
পাচ্ছ?
নাকি? শোনা যাচ্ছে তো?
In addition to this, if the norms of the vectors are 1 for all I, so if in addition, if all the vectors have uh, have norm 1, then this set will be redefined as orthonormal set of vectors. Then the set is called orthonormal. That is orthonormal set of vectors mean set of vectors. means if uh, any two distinct vectors are orthogonal, that is their inner product is 0, and if each vector is of norm 1, then this set of vectors are called orthonormal vectors. For example, in Rn, we know the standard basis, which is E1, E2, En. So the set of vectors E1, E2, En, where Ek equal to 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, where 1 is in the kth place. Yeah. So this is an orthonormal set of vectors in Rn. Because if you do the inner product Ei comma Ej, so what will happen with respect to the standard inner product? So just doing the component wise multiplication first and then add them. So thus we will get 0.0 plus 0.0 plus 0.0. At the ith stage it will be 1.0, and at the jth stage it will be 0.1. So all these are 0. So this is 0. And from their definition of EKs, the norm of EKs are all 1 with respect to the usual inner product. So this is an orthonormal set of vectors. Now, if an orthonormal set of vectors in an inner product space B forms a basis, then this will be called an orthonormal basis of B. And this will be called an orthonormal basis of V. So let us have some examples. Let us have a look at some examples. That is, you may check that the set of vectors 1 by root 3 minus 1 by root 3, 1 by root 3, 0, 1 by root 2, 1 by root 2, 2 by root 6, 1 by root 6, minus 1 by root 6. So is an orthonormal set. Is an orthonormal set of vectors in R3. So you may check. Now, if you consider the vector space C minus pi pi, that is a set of all those complex valued continuous functions defined on a closed interval minus pi to pi, equipped with the inner product f comma g. So this is minus pi to pi ft gt bar dt, and we all know that this defines an inner product on C minus pi to pi. Now in this vector space, if you consider the set of vectors, that is the set of functions, the first one is one function, and union, if you take En for all natural index n and Fm for m belongs to the natural number set n, where what is En? En is a function which is defined by cos nt, and Fm is a function which is defined by sin mt. This is true for all n comma m belongs to natural number set, and for all t belongs to minus pi to pi. Yeah. Now, now we can check that. We can check that number one, norm 1 square. Now, what is norm 1 square? That is inner product 1 comma 1. Now, what is the inner product? Inner product is this. So that is integration minus pi to pi 1 1 dt. Then what is the integration? Integral value, that is t minus pi to pi, that is pi plus pi equals to 2 pi. So in the same way, if you calculate the other norms for the functions en and fn's, then you will see that norm en square is pi, norm fm square is pi. Number two, the functions in S are all orthogonal to each other. Why? Just check it on your own, that what is inner product En comma Fm. This. What is inner product En comma Fm? Then you will find that this will be 0, because it will be integration minus pi to pi cos nt sin mt dt, and this integration is 0, as you can check. Number 3 is, just check this integration, cos nt sin mt dt. So you need to check this integral. And number 3 is, capital S is a linearly independent set. Linearly independent set of functions. Okay. So therefore, so if we are to make these functions orthonormal, so we must divide the first function 1 by root over 2 pi, the functions en's by 1 by root over pi, and the functions fn's by 1 by root over pi. So therefore, the set 1 by root over 2 pi union 1 by root pi en greater equal to 1 by root over pi fm n greater equal to 1. So this is an orthonormal set of vectors in C minus pi to pi. So this one. So I'd like to stop by proving just one observation, that the theorem is that if v1 v2 vn be a set of orthogonal uh, vectors, then they will be linearly independent. So this is an important observation that any orthogonal set of vectors will be independent, linearly independent. Why it is linearly independent? Because if you suppose that it can be expressed as the linear combination lambda 1 v1 lambda 2 v2 plus lambda n vn, and if this is going to be 0, null vector, then by taking inner product with some vk, with this one we will have, so lambda 1 v1 plus lambda 2 v2 plus lambda n vn comma vk. So this is equal to theta comma vk, and this is going to be 0. Now just expand this inner product by using the definition of an inner product. So just using this, you can expand it to, so it is lambda 1 inner product v1 vk plus lambda 2 inner product v2 vk plus dot 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 lambda k inner product vk plus lambda n inner product vn vk. So this is equal to 0. Now, since we have assumed that these vectors are the these vectors is a set of uh, is a is an orthogonal set of vectors, so that means they are orthogonal to each other. So therefore, their inner product is 0, except this one. So this expression will leave only the term lambda k inner product vk is 0, this one, and therefore lambda uh, k equal to 0, as we have chosen vk's are non-zero vectors. Okay, so that means this will be true for any k runs over 1 to n. So this is true for all k equals to 1 to n. Okay, so thus we see that if we assume that v1 v2 vk will be a orthogonal set of vectors, non-zero vectors, so then they will form a linearly independent set. Because when we are talking about linearly independent set, that is linear independence of vectors, then we need to take non-zero vectors, because a linearly independent set of vectors will never have zero vectors. So this is for the today's lecture.